How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at heterogeneous equilibria and KEQ. So our objectives will be to accurately set up the equilibrium constant expression and calculate its values for heterogeneous equilibrium, including saturated solutions. So remember how KEQ is unitless, and it was because the concentrations and the pressures are actually compared to a reference value. For pressure, that was a reference value of 1 atmosphere. For concentrations, it was 1 molar. And if this was my equilibrium expression, it's really the pressure of that gas divided by 1 atmosphere, and then the pressure of that gas divided by 1 atmosphere, and effectively just cancels out the unit for atmospheres, and we end up with a unitless number at the end. Well, an interesting thing happens when pure solids and liquids become part of our equilibrium. So let's take a look. Heterogeneous equilibrium. It's an equilibrium that involves different states of matter. That's the hetero part. So we got different states. So an example could be like NaCl solid being in equilibrium with its aqueous ions. They're in different states, so that makes it a heterogeneous equilibrium. There's aqueous and solid phase. So we could try to incorporate the concentration of NaCl solid into our equilibrium expression, but the standard that we're going to compare it to is the same thing. So for example, this would be what you might want to get right away. So the concentration of the ions divided by the concentration of the solid. But, the concentration of the solid, the reference that it's being compared to is the concentration of the solid. That's, the concentration of a solid doesn't really vary at all. If I have a chunk of sodium chloride over here and a chunk of sodium chloride over there, they're going to have the same concentrations. They're solid, same crystal structure. So when we compare them to the reference, they just kind of cancel out. And what we're left with is effectively not having the solids in our KEQ expression. And the same thing's going to happen with the liquids as well. So whenever you have these heterogeneous equilibrium, effectively the solids and the liquids drop out of the expression completely. So an important note, though, is that even though they don't appear in the KEQ expression, those pure substances must be present at equilibrium in order for it to be at equilibrium. If I'm talking about dissolving some salt and I didn't have any sodium chloride solid to start with, then you're not at equilibrium. If you don't have that sodium chloride solid, you're not at equilibrium. So here's an example. We have CaCO3 solid, forming equilibrium with CaO solid and CO2 gas. So what's the KEQ going to be? Well, remember how the solids drop out. So the KEQ is going to be the pressure of CO2 times, hey, that's a solid, so not going to include that. All right, divided by, oh, hey, that's a solid too, not going to include that. So the KEQ is really equal to the pressure of the carbon dioxide in this example. So do a little practice. Here's 3 problems. Try them out. Remember, solids and liquids drop out of the KEQ expression. All right, so for this one, KEQ is going to equal the pressure of CO gas. Oh, hey, liquid's not going to be there because it's a pure substance. Divided by the pressure of CO2 gas times by the pressure of H2 gas. So basically, any of the solids and liquids aren't going to be a part of our KEQ expression. So in the next example, we got tin solid and 2, hydronium ions that are aqueous, giving me, there should be an AQ there. Oops. And H2 gas. So the KEQ is going to be equal to the products, so the concentration of that tin 2 ion, plus the concentration of that H2 gas, I'm sorry, not plus, that's a multiply, divided by the, hey, tin solid, not going to be a part of it, so I'm just left with the concentration of H plus squared. All right, and the last one, we got H2O liquid and carbonate ion aqueous, giving me hydroxide ion aqueous and HCO3 minus aqueous. So again, KEQ is going to be equal to the products. I got OH minus to the 1 power times the concentration of HCO3 minus to the 1 power divided by, well, the H2O liquid isn't going to be a part of it. It's going to drop out. So I'm just left with the concentration of the CO3 minus 2 ion. So that's how you do those. summarize. Can you accurately set up the equilibrium constant expression and calculate its value for heterogeneous equilibrium, including saturated solutions? That's it. Goodbye.